In today's lesson, we're going to talk about using inverse functions. Before we talk about functions, let's talk about what it means to be an inverse relation. So in my top illustration, we see a relation between x and y. And we've plotted, or I have plotted on here, the x and y values as points on a graph in blue here, so we can see that these correspond with these. Well, an inverse relation is quite simply, we're just switching the x with the y. So whereas I have in my first relation x is 0, in my inverse relation y is 0. And here y is 6, but here x is 6. And so we continue that flip, if you will, or inverse, all the way through. And if we were to plot these points, we would see that it would look like this. And it would look like that. Now, one important thing to point out here is that these points have a line of symmetry, as do all inverses. And that line of symmetry is y equals x. So it reflects over the linear parent function y equals x. A couple other illustrations here. So let's look at some functions here. If my original function, again in blue, is f of x equals x squared, the inverse of this, the graph, is going to be simply reflected over that linear parent function y equals x, like so. And that's what happens when you flip the x's and the y's. And again, if we look at the parent cubic function, its inverse, when you switch the x and the y, is also going to be reflected over the linear parent function y equals x. So all inverses reflect over y equals x. Now, one thing that we're going to want to be able to determine is whether or not the inverse of a function is or the inverse of a function is a function. Now we can determine whether or not a line or a graph is a function simply by doing the vertical line test. But if we're going to do an inverse, we can tell by doing a thing called the horizontal line test. And so in my first example here, we can see in this first graph it's going to cross. If we draw a whole bunch of horizontal lines, it's only going to cross the graph at one point at any given point. So the inverse of this graph is going to be a function. The graph itself is a function, but the inverse is going to be a function. But in the second graph, though, even though that this passes the vertical line tests, the original graph is a function, the inverse is not, because it's going to cross at 2 points. So it's going to be more than one, so thus its inverse, when we reflect it over that line y equals x, will not be a function. So let's look at an example here. We're given that f of x equals 3x to the fifth minus 2. We want to determine whether the inverse of f is a function. Then we're going to find the inverse. So the first thing we want to do is determine if its graph is going to be a function. So let's go ahead and graph this. Here's my graph of that function, and it appears at first glance that maybe it's not, the inverse is not a function, but it actually is, because we can see right here it looks like it goes horizontal, thus causing it to fail the horizontal line test. But if we look at it a little bit more closely, I'm going to use the table here. So it seems to flatten out at -2. if I look at the table here, so it crosses the y-axis at 2. That's the y-intercept. But I went ahead and changed my table to count by 0.2s, and we can see that it does not, in fact, flatten out in -2. It's moving, but very slightly. So this does, in fact, pass the horizontal line test. Thus, the inverse is a function. So I'll start off by saying, yes, f -1x, or the inverse, is a function. Okay, remember, the -1 power indicates inverse. We used that before when dealing with matrices. Now we actually want to find the function. So I'm going to rewrite this using as y instead of f of x. So fifth minus 2. And the first thing I want to do when finding the inverse, remember in the table we switched the x and the y, and then we plotted those points. Well, here we'll do the same thing. We're going to switch, or flip rather, the x and y. So I'm going to have x equals 3y to the 5th minus 2. And now all I have to do is solve for y. So I'll add 2 to both sides, leaving me with x plus 2 equals 3y to the 5th. And then I'll divide both sides by 3, which will leave me with, I'm going to go ahead and flip this around, y to the 5th equals x plus 2 divided by 3. And I can't simplify that, and now all I have to do is take the 5th root of both sides. And since this is an odd index, I don't have to worry about plus or minus. So y equals the 5th root of x plus 2 divided by 3. And that is going to be my inverse function. Or we would rather write it like this. Inverse of f of x is 5x plus 2 divided by 3. So that's how we rewrite it in function notation. Okay, now inverse functions, let's just say we have functions f and g are inverses of each other. And we can prove that if we do a composition function, f of g of x is supposed to equal x, and g of f of x is supposed to be equal x. If this is the case, then the function g is denoted to be f inverse of x. So let's say I want to verify that f of x equals 4x plus 2, and f inverse of x is equal to 1/4 x minus 1/2. We want to verify that these are in fact inverses of each other. So we're going to do a composition of each other. So I'll start off by doing f of f inverse of x. So I'll write this as 4 times 1/4 of x minus 1/2 plus 2. So I'll distribute the 4, which leaves me with x minus 2, and then I have plus 2, and then the 2's cancel, leaving me with x. So that checks out. But it has to work the other way as well. So I'll also need to verify that inverse of f of x will also equal x. 1/4 times 4x plus 2 minus 1/2. So I'll distribute the 1/4. That's going to leave me with x plus 1/2 minus 1/2, and thus that just equals x. So it checks out. So therefore, we can verify that they are inverses of each other. So that is using inverse functions. Till next time, I'll see you on the flip side.